Hello and welcome to part 2 of chapter 11, our inference about a mean. To start this part 2 off, we're going to go into 11.4, which is confidence intervals for a mu. So much like chapter 10, we're dealing with confidence intervals when we're dealing with our t-test. So remember, we have 1 minus alpha at 100% confidence interval would equal this equation for mu, which is our x bar plus or minus our t of n minus 1, which is our degrees of freedom, comma, 1 minus alpha over 2, which is going to tell us our cumulative probability, multiplied by our standard error of x, which is notated as the standard deviation divided by the square root of n. So our typical point estimates plus and minus the margin of error formula. Our t of n minus 1, 1 minus alpha over 2 is from table B. You'll see the bottom row for confidence intervals. It's similar to the Z procedure, except it uses S instead of sigma, like we've talked about in the previous video. And similar to Z procedure, except T instead of Z, right? We're using a whole different type of test. We're using T-test now, not Z-test. And the alternative formula, just like we stated, I kind of wrote it up here. Instead of saying the standard deviation divided by the square root of n, we could just replace it with the standard error of x, and we know, since we don't know the standard deviation of a known population, we're just using it from the data set that we collected. So here's our confidence interval example from example 1. So let's calculate a 95% confidence interval for mu for the birth weights of the SID babies. So this one was from a previous example that we did in the last video, and in which we had a x bar equals 280, 90.5, our standard deviation was 720, and our sample size was 10 people, right? So now let's derive the confidence interval for it. So our confidence interval formula for mu is going to equal our x bar plus or minus our t of n minus 1 degrees of freedom, comma, 1 minus alpha over 2 multiplied by the standard error of x, which is notated as the standard deviation divided by the square root of n. So let's first work on our t interval here. So we know our n is 10, so this would be t of 10 minus 1, comma, 1 minus, well, if we were 95% confident, we know confidence and alpha go hand in hand with each other, so it's 0.05 alpha over 2. Move this along here, so if we do 1 minus 0.05 divided by 2, we know that's 1 minus 0.025, which is 0.975, right? And t minus 1, or 10 minus 1 is 9. So we're looking for a t of degrees of freedom 9, comma, cumulative probability of 0.975, which if you go to your book, you find degrees of freedom 9, go over and find the cumulative probability at the top of 0.975, you'll see that equals 2.262. Okay? Now, let's put everything else we know from the equation in. So we know our x bar is 2,890.5 plus or minus our 2.262 multiplied by the standard deviation, which is 720 over the square root of 10. When we multiply this out, with 2.26 times 720 divided by the square root of 10, you're going to get a value of 515.0212 plus or minus 289.5. So our confidence interval is going to be 2,375.478, comma, 3405.521 grams. So we would say that we're 95% confident that the true value of mu falls between 2,375.4788 to 3,405.5212 grams. So the true value, we were 95% confident that the true value mu falls in between this interval here. So very similar like we were doing before. I think the hardest part is just understanding how to get the t-value, but once you understand that, just like we were finding the z percentile, we're finding the t-value, t percentile for this as well. So here we have our confidence interval example number 2. Data are the percent of ideal body weights in 18 diabetics. Here's our data. Here's our 18 body weight examples. So based on this data, we want to calculate a 95% confidence interval for mu. So first thing you're going to do is we need to sum all them up and get an average. So if you sum them all up, it's going to be 2,030 and equals 18, and you're going to get your x bar to equal 112.7778. Your standard deviation is going to be 14.424. Okay, so we know our confidence interval. We're going to have to calculate the standard error of x, so we can kind of do that now to get it out of the way. So remember, our standard error of x is going to equal our standard deviation square root of n. It's equal to 14.424 divided by the square root of 18. You get a value of 3.3569. Next thing we're going to need to know for our confidence interval is our t of n minus 1, comma, cumulative probability of 1 minus alpha over 2, right? So we're 95% confident, and we have 18 individuals, so it's going to be t of 18 minus 1, comma, 1 minus 0.05 over 2. 1 minus 0.05 over 2, we know that's going to be 0.975, and this is going to be a t-value of 17. So we want to find t, degrees of freedom 17, at 0.975 cumulative probability. You go to the back of the book and you look that up, you're going to find that their t-value is going to equal 2.110. So now we just plug everything into our equation, where we have our x bar, 112.7778, plus or minus our t-value, 2.110, multiplied by the standard error of x, which is 3.3569. Multiply this out, you're going to get 7.083, plus or minus our x bar. And then you're going to get your confidence interval of 105.6948, comma, 119.8608. And we would say that we are 95% confident that the true ideal body weight for people that are diabetic will fall between these intervals. And that's how we find the confidence interval for this. So pretty straightforward. Next part is paired samples. So when we do paired samples, each point in one sample is matched to a unique point in the other sample. So much like when we're doing t-tests, we're comparing two different groups, right? But there's different types of groups. One type of group is called a paired sample, right? So each point in one sample is matched to a unique point in the other sample. This is what we would do like pre and post test, right? When you take a pre-test for a class or for an intervention, then a post-test, each point is one sample and it's matched to a unique point of the other sample, right? If you have someone who does a pre-test but not a post-test, it doesn't mean anything because you don't have a post-test. You have to have an n, so you have to have a pair for it. Pairs can be achieved via sequential samples within the intervals, like I said, pre-post tests, crossover trials, match procedures, also called match pairs or dependent samples, right? The post-test is dependent upon a pre-test dependent samples. So here we have an example of a study addresses whether oat bran reduces LDL cholesterol with the crossover design. Subjects crossover from a cornflake diet to an oat bran diet. These are the different points that were brought up for the exam. So half the subjects started on the cornflake, then half on the oat bran. They went 2 weeks on one, measured the LDL. They had a washout period to reduce it, the oat bran and cornflake from the diet. Then they did 2 weeks. They switched diet, then two weeks on the second one, the one that they weren't on, and measured LDL. So you had half the subjects on corn, then on oat, and then they flipped after this washout period, and then went back on the second diet, and then they were able to compare them to each other. So here you have your subjects and your cornflakes. On cornflakes for the LDL and their oat bran, see how each point, subject number 12 had a match point for the cornflake and oat bran. So the big part here is we want to calculate the difference variable, delta, which is notated by a triangle. It's a delta. Step 1 is create the difference variable delta. Let delta equal cornflakes minus oat bran. That's a difference, right? Difference, subtraction, difference, delta. Order of the subtraction does not materially affect the results, but does change the signs of difference. Remember, greater than or less than. Here are the first 3 observations. So here you have your first 3, and you just have them, and you subtract them out, and this is where you'll get your delta value. Positive values represent lower LDL on the oat bran. So here we explored delta values. Here are all 12 paired differences in the deltas. So these are all the delta brands. This is them represented as a stem plot. The shows a slight negative skew with a median about 0.45, with results varying from a negative 0.4 to positive 0.8. Here is your box plot. So a great summary. You can see your Q1, Q2, Q3, Q4, and your median where the majority of the data points lie. This is just a visual representation of it. So descriptive stats for delta. I'm actually going to pause the video here and then pick up this descriptive stats with the next part in the next video.